Start recording. All right. So now we have both. See, the frame is now gone. But I know, Zoom is still live and recording. So I'm not sure how I can tell whether Zoom is still around and working or not. Hmm, curious. All right. Yeah, I could do that. It depends on whether it reports as Zoom or it reports as something else. Yep. Yep. It does report as Zoom itself. So that helps. Okay. All right. So it is noontime. I'm going to get started. So today's focus, there are several things, but they're all related. First of all, we will hopefully get to the exam from fall 2024 today, because we need to have our own exam too, like soon. The plan is to have it next Wednesday, okay? But that kind of depends on whether I have time to go over the exam too. So the other thing we also have to talk about is the CNF homework assignment, which was due maybe a minute ago. Yes, less than a minute ago. So we'll talk about that one, and then there's a basically a additional homework assignment based on that one, so that you can practice more CNF conversion, but also resolution and how we use resolution to prove theorems. So that's kind of, but all of that is related to exam two because all of that is in the scope of exam two. So everything that we talk about today, I can say relates to exam two. All right. So with that said, we are going to take a look at the homework assignment and then do the derivations so that we can end up with a CNF based on the expression. So we are now in propositional logic. This is the homework that was due just a minute ago. And this is the expression that you need to convert into CNF. All right, so before I start, are there any feedback, comments about the homework assignment? Yep, go ahead. There are multiple ways to get to the CNF, and there are many resulting CNF that can also be considered correct. Which means some of those can be simplified, but I did not ask for the most simplified CNF. So as long as your answer is in the form of a CNF and it is equivalent to the original Boolean expression, it will count as 100%. Yes. Um, Other than it just has to be a CNF and I have to be able to, I need to be able to understand your answer, no specific format. Mhm. All right, so I'm just going to get started here. This is the original expression, which is the same as the actual mathematical notation, but personally, I prefer to use the simplified notation just because it's easier for me to type and it's a little bit more concise. But when you work on the homework assignment, you can choose to use any representation as long as I understand it. So that means, for people who just go like, okay, because CISP 360 is the prerequisite of this class, I'm just going to stick with C++ notation. That's okay too. It's just a little bit verbose from my perspective, but it's fine. All right, so I will start up my mouse pad here, okay? And this is, another window, which is fine. So what I'll do is I'm just going to copy and paste the original expression and then start deriving. There's a certain strategy to the whole thing. Um, so we'll take a look at the overall strategy. Some of that is pretty obvious. The Getting rid of implication is kind of what you have to do anyway. So might as well do it first. So I would just convert all the implications to something that involves negation and disjunction. So I would try my best to do one thing at a time, so this way it's not confusing. So I would do I'm handling this implication first. So it would be the negation of P or R and not T. Yep, no, does not matter. I don't think it matters. Okay. All right. So that's the first step. The second step is to get rid of the other implication, which involves the negation of the entire left-hand side. So this is where, not putting this on paper is helpful because you can just copy and paste. Now, when I uh, the nice thing about copy and paste is not just saving time, but also you're not going to copy wrong. Okay, that's the biggest thing about copy and paste is I just change the operator to a or, and then I go to the front at the first component and negate the entire thing. Hmm? And then we just apply De Morgan's law until you cannot apply De Morgan's law anymore. Okay, so De Morgan's law is one of those things. It's kind of like distribution for negation. Okay, in a sense. Okay, it's not exactly that, because as you distribute the negation from the outside to the inside, you also have to change the operator. If you're negating a or, then it becomes an and of the negated components. If you're negating an and, then it becomes a disjunction of the negation of the original components. But nonetheless, you're moving the negation to the inside, which means it is a one-way street. There's no way to get into a loop when you apply De Morgan's law repeatedly. Okay, so that means it's good because you're going to hit a dead end at some point. Then you can stop applying De Morgan's law. So now we are going to go apply De Morgan's law, and I see only one way to apply De Morgan's law right now, which is the negation of the or, which is here. So the way we do this, or the way I do it, is to write the components first, and then yeah, but then I apply the not to both components, and make sure that I change the disjunction into a conjunction. So this is a conjunction by implication, but if, for those of you who want to see the actual operator, we can use multiplication as conjunction. Or, since ampersand is also easy to see, you can also do that. But in my expression, I just, not even have a operator, just like in multiplication. Most of the time, you do not even write the multiplication operator. So the other side stays the same, like so. Okay. So now I can apply De Morgan's law at least one more time because I'm this negation here is negating this implicit and over here. So I have one more De Morgan's law to apply. But at the same time, I can also simplify the not p to just p. There we go. And then the other part now becomes not R or not T. So I can kind of combine the double negation to cancel out the double negation right here. So that's that. And then we have plus Q not S, like so. So in this case, I remove the parentheses because the operator priority is very similar to normal algebra. If you see multiplication and addition without parentheses, then the multiplication in this case is conjunction, has a higher priority. So that's kind of implicit. So I'll be still doing okay so far up to this point. Hmm? So next is to distribute. The question is how we are going to distribute. So this is where things you can make it more complicated than it has to be, or you can kind of go like, oh, okay, one more step and we are all done. Okay, so you have to think about the two distributions which are listed in the homework assignment. So if you go to the homework assignment and just go all the way down to distributive, we have these two ways of distributing. So now you have to think about which one makes it closer to a CNF. The second one, if it is applicable, will get you into a CNF, okay, or something that is closer to a CNF than the first one. The first one will give you something that's further away from a CNF. So now I want to go like, okay, maybe if I can, I would apply the second one. So let me go back to this one. So the second one looks like it is applicable, okay, because we have a CNF on one side. We also have a CNF on the other side. So when you go back to the distribution, if AB is a CNF and C itself cannot be a CNF, but this is where you can also apply something that you have learned in general algebra, which is FOIL, F-O-I-L. Okay, so as it turns out, FOIL also is applicable in Boolean algebra. So let me first explain, FOIL itself first, and then we'll talk about how to proceed from this step. So FOIL, the way you understand FOIL in normal algebra means if you have a plus c times, this is actual multiplication and addition, c plus d. FOIL means it becomes ac plus bc plus, oh, okay, let me be more systematic. AC plus AD plus BC plus BD. Okay, that's known as FOIL, which I cannot remember what it stands for. Okay, fine, we'll look it up. I know some people are, okay, what does FOIL mean in algebra? Okay, there we go. First, outside, inside, last. Okay, I don't really care about the name. I care about the derivation, okay? Because some people may complain and go like, but Tech, you did not specify FOIL in the rules, so how can I possibly know about FOIL? The thing about FOIL is it can be derived from the usual distribution. So let me kind of show you how we can do that. So in normal algebra, a plus b times c is distributed as ac plus BC, right? That's the most basic distributive law in normal algebra, which turns out to be also true in Boolean algebra. So now we go like, okay, but what if this C is C plus D? Okay, so now we say, okay, but this is C plus D. Fine. Okay, then this becomes just C plus D, and this also becomes just C plus D. So now we apply distribution again, okay? So once we apply distribution again, the first one, okay, let me put extra parentheses that are not needed, but it's useful for the discussion. So if I put in extra parentheses here, then the first pair of parentheses becomes AC plus AD because of the, the most elemental form of distribution. The second one becomes BC plus BD, also because of the most elemental form of distribution. In other words, FOIL is a consequence of the most elemental form of distribution. It is derived from just the most elemental form of distribution. Is that okay? All right. So yes, um, you can, yes, because of the priority of operators. So the priority of operators says that we have to perform conjunction before we perform disjunction. So there are implicit parentheses around these two. But because we mentioned operator priority, so the parentheses are not exactly needed. But for readability, it's always kind of nice to have the extra parentheses. Um, that is correct. You cannot factor. Yep. hmm all right. So this is the normal foil in normal algebra. So now we look into the other distribution in Boolean algebra, which is AB or CD, A and B or C and D. Okay, so let me put in extra parentheses. So applying FOIL to this one, then it becomes A or C, and B or C, and A or D, and B or D. For exactly the same reason that I explained FOIL, the normal FOIL, you can also do the FOIL like this in Boolean algebra. Is that okay? Does everybody understand how I derived the second FOIL transformation just for Boolean algebra? It does not work in normal algebra, but it does work in Boolean algebra. Is that okay? All right. So when we look at this particular FOIL, and then look at what we already have here, we go like, oh, this is nice, right? Because if I look at P as A and I look at this whole thing as B, I look at Q as C, and then I look at not as D, then one single foil and I end up with a CNF. Okay, so we'll go ahead and do this. So that means we have P or Q, and then we have um, Okay, I will use extra parentheses just for clarity, or Q, and then we have P or not S, and then we have not R or T, and then the whole thing or not S. Okay, so is that okay? Does everybody understand, how I carry out the FOIL and basically end up with, I mean, yes, we have to dissolve the unnecessary extra parentheses, but in the end, we now have a CNF. Yes, go ahead. The correct. Yes, we can. Because parentheses if you have a disjunction on the outside and what you are oring is also a disjunction, then by the law of association, associative law, we can also dissolve the parentheses. The reason why we can dissolve the parentheses is because being right or left associative, does not really change the meaning of the or. So, that means, the next step, if you want to make it look like a CNF or look like a proper CNF, then we can dissolve the parentheses. And I would even go to the trouble of ordering the variables so that they are in alphabetical order. You don't have to do that, okay? Because, it just makes it easier for the next step that we need to do. So now we have a CNF because we have a conjunction that has four components. Each component is a disjunction. Each component of the disjunction is either a variable or the negation of a variable. So now it has met all the requirements to be a CNF. Question? Yeah, that's fine. Yep, yep. You can have the extra parentheses. So to express this it has many other ways to express it. You can use, typical C notation if you want to. Okay, so this is Q or not R or T. Some people may have this representation because they have been testing, all the derivations step by step. I'm not sure if any one of you actually did that, but I introduced that method in the class. So, for those people who want to double check everything along the way, they would have something like this already to begin with, because they would have written a C program to test the equivalency of all the steps in between. Hmm? So in Python, I think the operators are spelled out, right? Okay, fine. Just use VI, do a search and replace, and then you have C code. Yep, so this is the C++ way of expressing exactly the same thing. So, yep, that is the whole answer. I don't see any way to simplify that any further, so this is it. Now, you might end up with an expression depending on, which route you took. You might end up with an expression that is a little bit longer. Okay, that's okay. As long as it is equivalent to this CNF, it's still okay, but it has to be a CNF. Yes. It does not matter because conjunction is commutative. Yep. So those are so in from that perspective, you can see that Boolean algebra shares a lot of property with just normal algebra. All right. So are we good with the solution of the homework assignment? All right. Excellent. Are there any questions about the derivation itself? This is one of many ways to derive this. Okay. You can also carry out the FOIL in the wrong way and end up with something that looks really ugly, and then you have to do a lot of simplification to bring it back to, what it's supposed to be, but it will still work. You can do this distribution that is not going to be helpful. It will take you further away from what you need. You can do that too. Yeah. Hmm. All right. So I'll be good with the solution to the homework assignment. Okay. All right. So now we can talk about the new homework assignment, which is, let me see, where is it? Let me go back to modules. It is now visible to you already. I released it sometime this morning, I think. It's called Resolution and Proof by Contradiction. And there's a similar homework assignment from last year, which was recorded, but the solution is not going to be helpful to people who watch the video because this is a different expression. So this looks a little bit uglier than what you already handled, but now that you have some experience converting Boolean expression into CNF, I mean, you just kind of have to work with this one. It's not, it looks really ugly, but once you start to work with it, it's not quite that bad. Okay. So the thing is, I want this to be my excuse me, phi, which means I want to know whether this is a theorem of this. This is psi. Okay, this is what is given to you to be true, and I want to know as a result, is this implied by this? That's the question. But the way I want you to do it is to do it by, okay, there are restrictions here. So you can only use CNF conversion, which means you convert something into a CNF, then you apply resolution repeatedly, and then utilize the concept of proof by contradiction in order to show me whether this particular phi is a theorem of what we just worked out today or not. So that's kind of your new homework assignment. Do we have any questions about the new homework assignment? Yes, that is correct. But you can only use the mechanism that I just talked about. So we are not going to be using the 20 something general rules for Boolean algebra. We're going to be using CNF conversion, which I just demonstrated today. And then once you have the CNF, then you apply resolution, and we either hit a dead end, which means we cannot quite get to false, but we cannot derive anything anymore using resolution, or we can resolve to false. So now you have to also look at that result and conclude using your own words whether phi is implying uh, excuse me, whether psi is implying phi or not. Okay, so that's your new homework assignment. It is due on Monday because we do have a weekend in between. Yep. So we okay. I'll throw out the terms and then you have to kind of sequence those terms. Okay. So there's proof by contradiction. There's a negation of something. There is a conversion to CNF. So, what are you negating? What are you converting into CNF? And how do you do the resolution? And how do you interpret the resolution? That's kind of the focus of the homework assignment. So try to read the homework assignment, try to read the notes, and also, if you need to rewatch the video. So the answers are all there. Okay, you just have to kind of make a connection of all of those things. All right. So are we good with the homework assignment? Okay. Excellent. So was the other homework assignment? Yes, go ahead. That's just one of the class recording. Yep. This year it's fine. I mean, you can always go back to the previous years. Yep. None of the content of previous year lecture is a secret because otherwise it would not be living on YouTube as a public video. So you guys are all welcome to watch as much video from my YouTube channel as you want for various purposes, not just for this class. I had a colleague, so I know this part has nothing to do with the class, but it's funny. I had a colleague who her husband passed away, and she could not fall asleep at night. So she turned to my lecture recording to use it as a mechanism to help her sleep. which I think most of you already know that my lectures tend to have that effect on people. But nice thing is there's no chemical process in watching the video, so you're not taking melatonin or anything like that. It's all natural, and you might wake up knowing something that you did not before you went to sleep. Who knows? Sorry. That's a perspective kind of thing. I cannot tell people how to look at things. Alrighty. So we are done with this one. This homework is due on Monday. So I would get on this one as early as possible. Okay. But today's lecture is actually important too because I just illustrated some fairly mechanical steps of doing this, and also the trick of the foil. Okay, so you kind of have to evaluate. Okay, when I'm all done with converting implications, and also when I'm all done with De Morgan's law, all that is left is usually distribution and also simplification. So depending on how you do the distribution, you can be further away from the answer, or you can be closer to the answer. So just kind of you can always give it a try. Okay, try it one way and it doesn't seem to work, then go back and try it the other way. That's the only way for people to learn how to you know do the algebraic manipulation. Yep. What is the sorry again? Um, so I worked out that particular phi from the actual solution, which is a CNF, and to reverse, so I basically went backwards. I look at the CNF and then I go like, okay, how can I convert the CNF back into something that I can present to you as a problem? I believe there was like 5 or 6 steps, but that's kind of but depending on your path, right? It might take you a longer path. Yep. It's kind of like, how long does it take to drive from Sacramento to, let's just say, Santa Barbara? If you take Highway 5, it's not too long. But, if you take Highway 1, it might take you a bit longer, okay? But you can enjoy the scenery along the way. That's, huh? Yes, but there are many ways you cannot really increase your speed because you'll be in a town, in a small town, where everybody drive excessively slow because it's a retirement community and so on. Yep. All right. So that's done. And now we can move on to the exam from last semester. Okay, so let's go do that. It is in the announcement. The attachment is in the announcement. So now we go here, exam 2 from fall 2024. And it's just a PDF this time. I did not have enough time to put it onto my tablet, which may not be a bad thing, because actually reading it here and then just typing the answer sometimes is a little bit faster than handwriting on my tablet. Okay. So just a few quick reminders. The time is always going to be the same as the period of a class. If you need to apply for DSPS accommodation, do it today, okay? Because your DSPS needs a certain lead time, so do it today. You are still allowed to bring any paper-based um, notes or books or whatever you want to bring. It just has to be on paper. Um, it's an individual exam, just like the usual, okay? So let's go ahead and take a look at the questions. And I think some people are feeling probably a mixed feeling about question number one. This question number one is not applicable to you because this is about olive null. Okay, so we're not going to talk about it. Some of you may say, I wish we have a question that easy this semester. Some of you may say the exact opposite and say, oh, this is hard. I'm, we are fortunate that we did not get a question this hard. So if you want to if you want extra challenges, but no, there are no extra credit associated, you can try to take on this, question number one, but it's irrelevant for our discussion in today's lecture. Huh? It's not asking you to rewrite h. It is asking you how do we do the inverse function of h. Oh, turn it into homework assignment for CISP 310? Now that is something I can think about. No, not really, because the multiplication is not implemented in the architecture, and multiplication itself is going to take up a lot of locations in that tiny little processor. So we can't do that. Cannot. All right, so we'll start with question number two. So question number two is a relation question, and I did remind you guys to review the relation topic and material before today so that you can have a kind of like an authentic self-assessment of where you stand in terms of understanding the topics related to the relations. So you're given a relation which is 0, 0, 0, 1, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, defined over X, which has 0, 1, 2 as its elements. Within the scope of this question, define function C0 Rx as follows. Okay, so this is the entire function. Okay, yes, it is a universally qualified quantified statement of blah 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 blah, not unsimilar to what you saw in exam one, but exam one has to do with functions, induct injection, surjection, and bijection. This test has to do with relation, which means, this is probably something related to one of the properties of relations. So now you probably want to have an inventory of what can we say about a relation. There's reflexive, symmetric, asymmetric, transitive, and also comparable. So those are the five elemental properties of relations. If something is reflexive, antisymmetric, and also transitive, it is also known as a partial ordering. If it also has comparable, then it is a total order, right? Okay, so you kind of have to keep those things in mind, because that's your inventory of things that I might be asking you about. Okay, so that's one. And here's the other one. C1 of Rx is defined slightly differently, and it is like this. Okay, all right. So the first thing we want to do is to figure out what exactly is C0. So C0 is saying for every element E in X, for every element F in Y. Oh, there's no Y. This is also supposed to be X, by the way. So my bad. This is also supposed to be X. And C0, oh, okay. So for every E in X, for every F also in X, there's no Y. EF as a two-tuple is an element of C0Rx if and only if ERF and not FRE, or not ERF and FRE. Okay, so the first thing you want to ask is, what does C0 return? What is the type that it returns? Because not knowing what type it returns is going to make everything really difficult. So the first thing you need to identify is the return type of C0 as a function. So what do you think it returns? By the use of operator related to C0, it's already telling you something about it. Not a tuple. Okay. What does this symbol represent? Okay, this one here. What does that symbol represent? Element of. Okay, so whatever is on the left hand side can be anything, because even a set can be an element of something. Okay, what about the right hand side? What is the type of the right hand side of element of? It has to be a no, it has to be a set. Very good. Okay, it has to be a set. So C0 as a function returns a set. So in this case, it is supposed to be returning a set of two tuples, where the two tuples returned in C0 will have to meet the requirement of, if it is a two tuple of EF, then it has to meet the requirement of ERF and not FRE, the whole thing, or not ERF and FRE. Okay? Um, but this is really just a shorthand for something else. Do you remember what it is a shorthand of? That goes all the way back to the module on relation. What does it mean when I say ERF? E relates to F, which is also known as EF as a two tuple is an element of R. Okay, so you have to make sure that you remember all the notations related to the whole discussion of relations. Okay, and notation is nothing more than just reading the notes, reading the module, and extracting and go like, okay, this notation also means that. Okay, so you have to get that first, okay, before you can even interpret what this means. Okay, so from this perspective, okay, even if I don't associate the expression, okay, let me highlight the expression here. So even if I don't associate this expression with one of the properties of a relation, can we figure out the answer? In other words, not knowing exactly what property we are referring to, reflexive, symmetric, asymmetric, transitive, or comparable, do you think I can answer the question? Or should I be able to answer the question of um, what is C0Rx? Well, the answer is yes. Okay, I should be able to do it because I should be able to look at all the possible pairing of elements of R of X with, so I should be able to look at all the two tuples of X Cartesian product with X and then evaluate the expression that is highlighted to determine membership of C0 and using Rx as parameters. Okay, so I would do that once, okay, but I think you should be able to do it yourselves too. Yes, that is correct. Yep, and vice versa. Okay, so what I'm going to do, is to look at all, let's say, oh, by the way, what is the cardinality of X Cartesian product with X? I just asked you a question that has to do with the definition of terms in set notations. Okay, cardinality, Cartesian product. Okay, what do those things mean? So can someone tell me what is the cardinality of X Cartesian product with X? Mm, no. Okay, so what is the membership of X Cartesian product with X? So let's start with that. So we are gonna so X is 0, 1, 2, and we want to perform a Cartesian product with 0, 1, 2. So what is the membership of the result? Well, good thing the test is open book and open notes because you can bring the set notation notes with you and look it up during the exam. Now, do I recommend taking the exam that way? No, because I would be assuming that you guys already know what is the Cartesian product of two sets. So this is my hint of telling you guys you need to get the notations down. Okay, you don't want to spend your time in the exam to look up the notations. You need to have those really handy. If you cannot remember everything, fine, not a problem. But copy and paste the notations to your own notes and kind of put them into one single area so it's easy for you to look it up. Okay. All right. So the membership of the Cartesian product is 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, and then finally we have 2, 0, 2, 1, and 2, 2. There we go. Okay, is that kind of reminding you guys what Cartesian product is about? Okay, so as I said, okay, the test was made having the assumption that you already know that before the exam. So that means, you don't want to waste your time to have to look up the definition of notations during the exam. Is that okay? All right. So now the question is, if I look at this in your Cartesian product, let's call that, let's give the set a name. I'll call it set A, okay? Okay, so we look at all the elements of set A, and then we look at the expression that I was highlighting, which is this one here, and I'm looking at a tuple EF. I just need to evaluate this thing and see if it is correct or not, see if it's true or not, okay? So now you can do this mechanically, okay? If you do this mechanically, it's going to take you some time to figure out the answer because we are not wired to perform really mechanical operations with precision. So the other way to look at this is to look at this expression and say, okay, semantically, what does it mean? Well, it looks like it is saying if one R 1R2 and not 2R1 will meet this requirement because this is an OR. Huh? Nope. It's not looking for anti-symmetry. It is looking for the negation of symmetry. Can I find one but not the other? So it is looking for the negation of symmetry. It's looking for evidence that the relation itself is not symmetric. Okay? So So that's kind of my hint, okay? So when you look at the relation R here, do you see that it has evidence that it is not symmetric? I see two at least, because 0, 1 is in the set, but 1, 0 is not. 2, 0 is in the set, but 1, 0, 2 is not. So that means in this particular case, C0 would be returning a set with two elements. One element is going to be 0, 1. The other element is going to be 2, 0. Actually, it has four elements because 1, 0 is also one of the elements, and then 0, 2 is also one of the elements. So let me just write it down. Okay, so I would say for Q2, C0 Rx is going to return a set where 0, 1 is in the set, 1, 0 is in the set, uh, 0, 2 is in the set, and then 2, 0 is also going to be in the set. Are we doing okay so far with C0? So let me see if I can arrange everything so you can see both. There we go. Okay. So you can now see the definition of C0, and you can also see the actual answer of what C0 is going to return. Are we good so far? Yes? No? Okay. All right. What about C1? Okay, C1 is defined in a similar way, okay, but this time we have three variables. I think that is a dead giveaway of what it is about, but I'm going to talk about it anyway. So this one says, for every E in X, for every F in X, for every G in X, EFG as a three tuple is in C1 of Rx. This X is supposed to be uppercase. If and only if the negation of ERG and the non-negative version of ERF and the non-negative version of FRG. Okay, so I think most people can look at this and go like, oh, I think it is related to transitive. That's right, because the transitive qualification is the only one that involves three variables. Okay, so that's more or less a giveaway. So once again, C0 is asking for examples that R is not transitive because it is confirming that ERF is true, FRG is true, but not ERG. So that means it's looking for evidence that R is not transitive. Okay. So the to do it mechanically, this one is brutal because there are three ways to choose E, three ways to choose F, and three ways to choose G. So if you do it purely mechanically, there are 27 items for you to evaluate. So it is best not to look at it that way, but to look at it as, okay, can I find some evidence that this particular R is not transitive? So what do you think? Is it transitive or not? I'm looking at it right now. Yeah, okay, that's good. It is not transitive. So, yes, I just applied the eyeball algorithm and have determined that it is not transitive because 2, 0 is present, 0, 1 is present, but 2, 1 is, oh, 2, 1 is actually present. Okay, never mind. Okay. Um, 1, 2, 2, 0. Okay, so this is the other one. It's right next to each other, so it's easy to see. 1, 2 is present, 2, 0 is present, but 1, 0 is not present. So it is not transitive. But the answer to C1 is not that, right? So C1 in this case of Rx would include the three tuple, which in this case would be 1, 2, 0. That would be one of the elements in C1. Okay, so let me see if you guys understand why we have a three tuple in C1 because it has to do with how C1 is defined. We are asking for EFG as a three tuple. It should be in C1 if and only if ERG, not ERG, and ERF and FRG. So by this definition, the every element in the set returned by C1 has to be a three tuple. Are we doing okay so far with that? Okay, I see some people nodding. Okay, and what about the rest of the class? Okay, so is that because of a question about the notation itself? Yes, go ahead. Mm-hmm. Mm-hmm. So what you're looking for is something. So the first tuple is gonna the second item of the first tuple acts as a connector to the second tuple. So you need the first. Okay, let me look for one example that works. Okay, so 2, 0 works. Okay, so when you look at 2, 1 as the first tuple as EF, I need something that starts with a 1 and then with a 0 as the second component. Nope, that's not the example I'm looking for. Let me look. I'm trying to look for an example that works. Oh, this one works. Okay, so if the first tuple EF is 0, 1, then I'm looking for something that starts with 1 and then something. And here is 1, 2, right? So now you can evaluate and say, okay, 0, 1 is present, 1, 2 is present. Is 0, 2 also present? The answer is 0, 2 is not present. So now that means 0, 2 is that means 0, 1, 2 is another element in this particular set. Do you is that working? Okay. So there's no, I mean, the mechanical way is to look at, there are three ways to choose E, and then for each way of choosing E, there are three ways to choose F, and then for each way of choosing E and F, there are three ways to choose G. So the only mechanical way is to look at all 27 possible ways to find your D, F, and G. But the eyeball way is just, kind of quickly, try to see if something is missing. Yep, triple loop. Yep. triple nested loop, and then each loop has three iterations, and therefore 27 possibilities to evaluate. Yep, 1, 2, and then 0, 2 is missing, so it meets the requirement of this part here. This is the requirement. Yep. So you can look for some other ones. Okay, look for ones. Let me look for one that is not going to meet this requirement. Um, oh, here's one. 2, 0 is here. 0, 1 is here. But 2, 1 is also here. So that means 2, 0, 1 does not meet this requirement, and therefore it is not a member of the set returned by C1. So is that working? Okay, all right. Hmm? Well, it depends on how the question is asked. So let's read the question carefully. The question is asking what is blah. So that means you need to have all the members in it. Now, what if you have some of the members listed and some of the members you just couldn't spot? I'll give you partial credit, like most of it. Is that okay? All right. So what I said a little bit earlier, that the worst case of evaluating C1 is 27 cases, is not entirely true either, because we already know the membership of R, which means the worst case is really just this thing squared, which is actually worse than the other way. Never mind. Okay, never mind. I said that. All right. So are we good with what C1 and C0 should be? Okay. So now we try to go back and answer the question 1 and 2. If the cardinality of C0 is 0, what relation property is confirmed about R over X? We just kind of talked about it. Yep, it is symmetric. And then for the second one, if the return set of C1 is empty, then what relation property is confirmed? Transitive. Very good. Yep. So that would be the actual answer to this question. Um, do you guys want the key to this particular exam? I can give you that too. Okay. So let's do that. Uh, okay, go to announcement. This is the key to exam 2 from fall 2024. See attached. And there we go. And now I can double check my own answer. All right, so let's double check my own answer and see if I got it right. Okay. Yep. So those are the two elements of C1. One confirms it's symmetric. Two confirms it is transitive. Huh? There's one more? One more of what? No, I think these are the only two that I figure out. So let's go back to my notepad. Yep, those are the only two. No, 0, 2, 1 would not work because 0, 2 is here, and then 2, 1 is here, and the 0, 1 is here. Yep. All right. Are there any questions? You can, yes, go ahead. Um, you look at, so you mean for the first element that is listed here? So with this one, it means I can find 1, 2, I can find 2, 0, but I cannot find 1, 0. Because the three elements, one is bound to E, 2 is bound to f, 0 is bound to g in the expression. Yep. So that's kind of going back to the exam itself. Where's my exam? Oh, I lost track of which browser has the exam already listed. This one is just a key. Huh? I, I'm not sure how a graphing calculator can be helpful other than it is programmable. Mm, well, the test is really checking whether people know how to do this and not so much whether they can find someone who can give them a program that knows how to do this. And there's no way for me to know whether you wrote the program yourself, which to me is fine. Okay, if you can write the code to do this, I can go like, okay, if you can write the code to do this, you probably understand the material, but there's no way for me to differentiate whether someone who wrote their own program on their own calculator or they just ask someone else to go like, hey, do you have a program that can do this? Can I borrow it or can I have a copy? So the answer is no. I cannot authenticate whether you actually wrote your own program or not. That's the, yeah, that's the hang up. All right. So getting back to the questions. And no, okay, there we go. Okay. All right. So to answer these questions, how do you prepare yourselves for the exam? Already knowing that your questions are probably something involving the same kind of topic. In other words, there'll be quantified expressions, and if so, for whatever reason, they relate to the properties of relations. So knowing that ahead of time, how do you prepare for the exam? I can tell you one thing. I personally do not think this is going to help, but that's my belief. Okay, that's just me. So how do you prepare for this exam, knowing that you need to fully understand quantified expressions, you need to understand set notations, and also properties of relations. So already knowing all of that, how do you get ready for the exam? Yes. Sorry. No probability in this exam. Yep. Probability is not in the scope of this exam. Yep. So the final exam is about graph algorithms, which is A star and Dijkstra algorithm, and also probabilities. So those are the topics in the final exam. All right. So to answer my own question, okay, so I will attempt to answer my own question, is really kind of go back and make sure that you fully understand, how to read quantified expressions, the set notations. So all of those are prerequisites to understand, to be able to start to work on the questions. Okay, so I would definitely do that. Okay, all right. So moving on to question number 3. Yes, go ahead. Okay, to those of you who think I'm talking to myself, I'm talking through the Bluetooth headset with one of the people who is online. So the question was, what is the scope, basically of the exam? It is everything after the first exam, up to and including propositional logic, but excluding probabilities. Is that okay? Okay. All right. So now we look at question number 3 and see if we can answer this one. Okay, so you can see that the some of the functions are recycled. So C0 is completely recycled here. And then C1 is, I believe, something that's new. Okay, so we'll work out what this C1 is related to. It's one of the properties of a relation, but the question is, which one are we talking about? So most of the definition of the functions is defined in this particular manner, which is using a quantified expression to say for every e in x, for every f in x, EF as a two tuple is an element of the return value of C1 of Rx if and only if blah 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 blah. Okay, so now the real part that you need to understand is what is the blah 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 blah, which I will highlight so that we can focus on just that. Okay, so for this particular C1, the focus is on this, which says ERF and FRE, and E does not equal to F. So now you have to remember which property of a relation has some of the same kind of elements in it. It is antisymmetry. Yes. Okay. No, antisymmetric is fine. One is a verb, one is no, one is the adjective, and one is a noun. So that they're fine. So it is antisymmetry. Okay. So a relation R is antisymmetric if and only if C1 returns an empty set, because this is also looking for a contradiction or looking for counter examples. So if the counter example size or the set of counter examples is not empty, then we have found at least one counter example, which means the relation is not anti-symmetric. Okay. So to answer the questions, number one is easy because we can just recycle the same answer from question number two, which means it confirms that it is um, no symmetric. This one is about symmetry. Yeah, this one is about symmetry, and then the second one is going to confirm that it is anti-symmetric. So now we only need to work out C1, the actual value of C1 and the actual value of C0. So we'll work with C0 first. So the question is, um, what evidence do we have that this particular R is um, not symmetric? Well, the only one that is qualifiable is 2, 1. But if you put 2, 1 in the set, 1, 2 also has to be in the set. Because the way this expression works out is you can flip and it will still work. So that means the actual membership of C0 is 2, 1 as a tuple, 1, 2 as a tuple. So it has two members in the set returned by C0. The set returned by C1 is, sorry? No, it is empty. It's an empty set. In other words, this particular R is actually antisymmetric. 2, 2 does not meet the requirement because 2, 2, if E is 2 and F is 2, then we can confirm that ERF is true. We can confirm that FRE is true, but then we also confirm that E does not equal to F is false, which means 2, 2 is not a member returned by the set of the set that is returned by C1. Correct. So C1 is collecting counter examples of elements in R to show that R is not antisymmetric. So for anything that is antisymmetric, the set returned by C1 is going to be empty because we cannot find counter examples. Yes. Um, the whole point is I'm not spelling it out, and you have to find the association. So in this case, okay, only one of the properties has equal to in it. So this tells me that you may need some time to review, right? Yep. Yes, that is correct. If R had 1 2 in it, then well, okay, if it had 1 2 in it, then C0 would return an empty set because it would be symmetric in that case. But then C1 would return the two elements, which is 2 1 and 1 2. Yep. Hmm. All right. Any other questions about number three? Number four is very similar in nature. Okay, so the only thing we have to watch out for is do we get something new in this case? So this one does get something new because C0 is defined a little bit differently, okay? Not like something that we have seen before. So this time it is defined like this. So to spell it out, for every E in X, for every F in X, EF as a tuple is in C0 if and only if blah, 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 blah. Okay, so the really important part is this blah, 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 blah part. So what is this one saying? It says E equals to F, and I use double equal to kind of make sure that it is a comparison. E equals to F implies EF as a two tuple is not in R. Okay, so which property of relation do you think this one maps to? Transitive typically require three elements, right? Three things because you need the first, you need the last, and you also need a bridge. So you typically need three things in order to know whether something is transitive or not. This one says E equals F implies EF is it implies it is not the case that EF is in R. So it's looking for counterexamples of a particular property. Which one is it? This one I intentionally make it very deceptive. Yes, go ahead. Reflexive. Yes. So reflexive usually only requires one single variable, but I intentionally make this one look a little bit different because what this means is if you choose E and F to be the same, how many ways can we choose E and F to be the same given that X has 0, 1, and 2 in it? Exactly three ways, right? E is 0, F is 0 is one way. E is 1, F is 1, second way. E is 2, F is 2 is the third way. In other words, there are only three things you truly have to evaluate in this case. Because for all the other cases, E and F are not the same. What happens when the left-hand side of the implication is false? What happens to the value of the implication? The whole thing is true. Okay, so that means those are non-concerns to us. The only concern is when E and F are both 0, they're both 1, and they're both 2. So the implication says, okay, if they are the same, then we want to make sure that EF is not in R. So that is exactly the negation of what it takes to be reflexive. Is that okay? So now we look at the set that is given to you, and we go like, what is missing? If I want it to be reflexive, what is missing? 0, 0 is missing. 1, 1 is also missing. So those are the only two elements that should be in the set returned by C0. And then the answer to part one is it confirms R is reflexive. The second one we have seen already. This one is about, oh, okay. This is bad because I messed up the formatting. Let me see if I can remember what it is supposed to be. This is also supposed to be something new because there's no G in here. I think it is I cannot remember. Oh, I know what this one is. Um, I think this is supposed to be part of the negation. Mm, okay, so let me see if I can. ERF implies FRE. I think this is supposed to be a negation. Okay, so let's work with that. Okay, see if that works out. So EG is supposed to be negation because I forgot to put a backslash in front, an additional backslash in front of the N, and that's why it only spells out EG without the N. Okay, so let's just say that that is negation. What is it trying to confirm in that case? Hmm. Hmm? It is not symmetry. We got symmetry already. We got anti-symmetry already. We got reflexive, and we also have transitive. So that means this one has to be comparable. Okay, so let's see whether that makes sense or not. So this negation is negating ERF. This negation, on the other hand, is negating the entire um, implication. So it is saying that if ERF, okay, okay. First of all, is this um, comparable? It should be pretty clear that it is. Is it comparable or not? What does it mean to be comparable? Huh? The last. Oh, okay. Oh, even with that covered, you should be able to answer the question. Is it comparable? What does it mean to be comparable when we talk about the relation? Comparable means every element relates to every element in some way. So that means if you choose 0 and 1, for instance, either 1 R 0 or 1 R 0, 1 R 0. So they have to relate to each other. The direction is not important. So one thing that comparable implies is reflexive. Everything that is comparable has to be reflexive. This one is not even reflexive. So we know for sure it is not comparable because it is not even reflexive. So knowing that it is not reflexive, now we plug in E and F being exactly the same. Okay, so let's say E and F are both zeros. Okay, so what happens here? E is 0, F is 0, ERF is false, right? The negation of false is true. And then we have true implies false, which means the whole thing is false. What? Okay, let's do it one more time. This is false. The negation of that is true. This is implying false. Okay, yes, the implication is false. And then we negate the implication itself, which makes it true. Okay, so it's not comparable. I have to remember what this EG is representing. I just cannot remember. Do you guys want me to spend some time to look at what the EG is supposed to be? Okay, it is. Yeah, I have to look at the question generator markdown representation, which I can get back to. Okay, so give me a second. And this is also kind of giving you guys a window into how these questions are generated in the first place, which I don't think is going to help you in terms of knowing what next Wednesday is going to have because I have not made those questions yet. Uh, yes, so exams, um, class 440, and then 1249, which is the semester. This is 1249-x2.js. All right. Yep. So we are looking for negation. Nope, there's no negation. I might have fixed that already. Okay. Oh, let me go back to the question itself and see if I can get some clue. Because I'm looking for some patterns here, so I can use that to help me find the expression itself. So ERF implies FRE. Okay, so we can do that. What happened to my prompt? Oh, right here. So we have ERF. Oh, this must be generated by some other script. Okay, so that's fine. Um, this is x2q1jan. So I have a separate program to generate the entire group of questions. There we go. All right. It's not this one. Not this one. Not this one. It has to be this one. Okay. So I was right. It was supposed to be a negation. Hmm. Hmm. Okay. So this is supposed to be a negation. So negate ER, not ERF implies FRE, and then we negate the whole thing. So if EF are both zeros, then we have false implies, no, we have true implies false. Okay, let's pick another one. Let's pick 1 2 2 1 2 2. So 0 2 is also missing. So let's pick E as 0 and F as 2. Okay. So 0 RF 0 R2 is missing. So the negation of that, so this is false, not false is true, and then we have imply, this is also false. So we have uh, true implies false, which means the implication is false. And then this negation negates the whole thing. So, I have to work this out maybe some other time because okay, I can also cheat. So I can look at my answer. Okay. And so we do have comparable here. So 0, 0, 0, 2, 1, 1, 2, 0 are all elements of that particular set. So what am I missing? I will deal with this and see if I can come up with an answer. We got 5 more minutes. And this is question number 5. Question number 5 is more of a chore than anything else. I give you a psi, which is a Boolean expression. I give you the entire truth table. You just have to evaluate um, the expression psi for every possible way that P, Q, and R can have values. So that's pretty much the idea of question number 5. And then question number 6, if we go back to the question. So question number 6 is similar to your current homework assignment. I give you the psi, I give you the phi, and then you have to use resolution to show me whether the phi is a theorem of the psi or not. But in this case, I simplify things quite a bit because you can see how everything is in CNF already. So that means the conversion to CNF should be a trivial step in this particular version of question number 6. So then the rest is just resolution. The resolution steps are shown in the key. So this key is showing you the resolution steps. And the answer is it does get to a false, which means phi in this case is implied by psi. So the way we read the key is like for this line, this is step number 5. It is basically saying 0, which is not Q or R, and 1, which is P or not R. They can resolve, and the result of the resolution is P or not Q. So that's how you read the mechanically generated answer. So yes, I kind of cheated because I actually wrote a program to perform the resolutions until either it hits a dead end or it gets to false. But these are the mechanical steps to get to false in this case. So you can probably figure out a faster way to get to false if you can just kind of eyeball and think, oh, okay, these things can link together and then they will lead me to false. But the more mechanical way is just this, which is not wrong. It just takes a little longer. All right. Is that okay? So I will get back to the um, yeah, but the property is called comparable. Yes. So I'll get back to the comparable one, because I need to double check and make sure that it is the solution makes sense, right? Okay. Yep. It's next Wednesday. So you can still ask questions related to the test on Monday. Yep. And also we can talk about the solution of the homework assignment on Monday because that is still in the scope of exam 2. Yep. next Wednesday. Yes. So the exam is next Wednesday, which is already kind of spoken here. All right. So it is supposed to be the 21st. We'll probably. Oh, okay. Well, since I mentioned this already, we'll postpone the exam to the following Monday. Okay. Yeah. Hmm. On the 21st. Yes. Yep. Oh, yep. So I take it back. It's not next Wednesday. It is the Monday following that Monday. Huh? 21st. Yes. 21st is the correct date. Huh? Yeah, sure. I can give you the other one. I gave you one already, so you're asking for one more. Yeah. Mm-hmm. You're just putting that. Yeah, that's a good idea. Yep. Yep. So, but does it take the expression already expressed in Python, or do you convert it from some other format first? Do you have a parser? You do not. Okay. Yeah. Okay. Gotcha. Uh-huh. Mm-hmm. Mm-hmm. It's slightly strongly typed. Mm-hmm. Mm-hmm. Okay. All right. Ryan, question? Uh-huh. No, because we already talked about the solution, so I cannot, people cannot make that up. Yeah, so the homework, typically are very low point value compared to the exams. So it really is just a way for people to practice so that they get ready for the exam. So I don't think, that is going to impact your overall grade at all. Yeah, I cannot guarantee that you won't be right at that border, but if you look at all the homework assignments, they all add up to 20%. Yeah, so it's not. Yeah, yeah, I cannot. There's no way to make up for it. Yeah, sure. Okay. Before class? What about before this class? Ah, okay. Okay, well, send me the time availability, your availability, and then I'll take a look and see if I can see if there's an overlap. I think there will be some overlap. Yeah. Mm-hmm. Yeah. It's the following Monday, it's the 21st. Yeah. So basically you got extra time compared to the announced date. Yeah. Well, this is like, next Wednesday too, right? So, hmm oh, I have to remember to stop my Zoom. My Zoom is still recording. Not that, people are really. Hmm? There's one right next to the bathroom. Yeah, but it's not filtered water. I think it's really just tap water. Except it is refrigerator. It is cold enough that you cannot tell the difference. Huh? Yeah. Yeah. Bottled water is actually worse than tap water in many, many cases.